talks. Today, it's a great pleasure to introduce Professor Chris Heil, a Georgia Tech mathematician, as you can see, or as you could see for a moment, who will talk about absolute continuity and the Banach-Zaretsky Theorem. As always, I would like to ask everyone to mute yourself and unmute yourself to ask questions during the talk. Chris, the audience, all yours.
Oh, thank you very much. Appreciate the invitation to speak, and I'm going to take the opportunity to give a shameless self-promotion of my text on real analysis. This talk is dedicated to John, and in particular, it starts with the text that he wrote. I think it was 1976 when it came out, Real Variable and Integration. And here's the Zentralblatt review of it. And the red part is what's really interesting. Why did John write this book? And he says that it's because none of the other texts in the area of analysis at this level stress the importance of absolute continuity. And I didn't appreciate that when I was a grad student. I didn't learn out of John's book, but over time, I really fell in love with absolute continuity as well. And I should mention that there is a new edition by John and Wojtek, came out in 2009. So a wonderful book that I hope you all will go out and buy in addition to my book. Eventually, it did become time for me to write my own book. Just accumulated many notes over the years and decided that I wanted to do it myself as well. And the goals for my book, what I wanted was to write a course, a text that really was for a first course. This is aimed specifically at people that have not seen Lebesgue measure, Lebesgue integral, dominated convergence, absolute continuity, right? People that are encountering this for the first time. And of course, I want what everybody wants. I want to be rigorous and complete, and I want to be clear, well motivated. I wanted my proofs to be enlightening. And then the discussion gives background, context, whatever, and I have lots of exercises. And in this talk, I want to talk about my successes and failures in the enlightening part of the issue. And the hardest part for me, as it turns out, is centered around differentiation, bounded variation, and absolute continuity. Those are the places where I really had to struggle in the text to give what I felt were enlightening proofs. And by enlightening, I don't mean short or just one-line things, but proofs that really, when you read them, they may be long, but they make sense, and they give you insight, and you see what's going on. And I'll tell you what I had difficulty with. Now, everybody's different, so certainly you may feel very differently about what is important in the field and what is not, or what you stress when you teach the course. But let's go all the way back to the fundamental theorem of calculus. One of the best talks I ever heard was by Robert Pfefferman at a true FFT. I was sitting in the colloquium room at Maryland listening, and he started his talk with the fundamental theorem of calculus and ended up in just step by step, took us to multivariable Fourier series, and it was just amazing. I'm not going to go to such heights today, but I am going to start with the fundamental theorem of calculus. And of course, the one that we learned as undergrads is that if you have a function that's differentiable and the derivative is continuous, then the fundamental theorem of calculus holds. The integral from a to x of f prime is f of x minus f of a. And this makes sense as a Riemann integral because we've assumed that f prime is continuous. And a basic question, does this hold? Once we learn about Lebesgue integrals, does this hold if we just assume that you're Lebesgue integral, right? Can I just put a Lebesgue integrable function in there? If f prime exists almost everywhere and f prime is integrable, will that equation hold? And one of the things I enjoy about teaching analysis, it's a subject where you get to show the students things that are obvious and false. and also things that are obvious and true, but sometimes the fun ones are the obvious and false ones. And this is one of them. It seems, or at least it seems to me when I was a student, this would have to be true, right? But of course, one of the first things we learn when we get to this question is the Cantor-Lebesgue function. And that's a counterexample. This function is constant on intervals, and the length of those intervals adds up to 1. So on any one of those intervals, the derivative is 0. So this function's derivative is 0 almost everywhere. And yet, call it phi of 1 is 1, and phi of 0 is 0. So it got all the way from 0 to 1, but the derivative was always 0 all the way across. So very, very strange. Function like that, whose derivative is 0 almost everywhere, is a singular function. Now, just for fun, I want to put up another function that I only learned about a few years ago. It's called the Minkowski question mark function. I learned this when Walter van Osch came and visited Georgia Tech and gave a seminar about this function. And it looks so much like the Cantor-Lebesgue function, except it's kind of like a somehow smoother version. And it's called the slippery double staircase. It satisfies a certain functional equation that's down there. And there's a paper by Walter that is a good introduction to this function. It's just fun. But let me go back. So we're going to talk about differentiation and absolute continuity. And I want to give you a theorem that's very important in the development of this topic, and whose proof is, I feel, really enlightening. And this is the simple Vitali lemma. You choose any collection of open balls and let U be their union. Okay. Out of all these balls, then you can choose finitely many that cover a lot of the union. In one dimension, you can essentially cover a third just from finitely many disjoint balls. And in higher dimensions, it's 1/3 to the d. The precise statement is there. And how do you prove this? You have this, possibly enormous collection of balls. You do a little pre-processing, and then you do the definition of a greedy algorithm. So the pre-processing is you choose a big compact set. That's almost all the whole set U. And then because it's compact, it can be covered by finitely many balls. And then you just start being greedy. Reach in there, choose the biggest ball. There's only finitely many. Choose the biggest one, right? Out of all the ones left over, choose the next biggest one and keep going. And that gives you your collection. And why? Well, it's certainly disjoint. And why does it cover everything? Proof by picture. Once you've got a big ball, any other ball that intersects it will be covered if you just blow up that first ball blow up the radius by a factor of 3. And that's where the 1/3 to the d part comes from, right? You're getting a fraction of the blown up covering. The blown up covers will cover everything, and you've only got a fraction of it. But it's a specified fraction, 1/3 to the d. So I really love this theorem and the proof. It's just nice. It's really nice. And from this, it does take work, right? But again, with what I think is an enlightening theorem, you use this to prove the Hardy-Littlewood maximal theorem. And then again, with work, but enlightening work, in my opinion, you go and you prove the Lebesgue differentiation theorem. Now, and we'll use Lebesgue differentiation later. But in essence, right, this is Lebesgue differentiation. You can trace it back to simple Vitali. Now, there is a full Vitali covering lemma. And in there, you put more restrictions on your set of balls. You have a set E, and you insist that every point in E be covered by a ball of arbitrarily small radius. So you have a collection of balls, but they have to shrink, right? They have to get arbitrarily small and still cover every point in E. So if you have that many balls, and you can take them smaller and smaller and smaller, then maybe it's not so surprising that you can cover a lot of your set with finitely many disjoint balls. And that's what Vitali covering lemma says. And again, precise statement right there. You can, within epsilon, you can find finitely many disjoint balls that cover most of E. Now this proof, this theorem, okay, the statement makes sense. And the proof, well, the proof is long. But in essence, it's still a kind of greedy algorithm. There's no largest balls anymore. You have to modify and kind of be sufficiently greedy. But I included the proof. I just copied it from my text. Okay. And all right. It kind of goes on, and you do something with half a radius and twice a radius. And okay. It's long, and I don't find the proof particularly enlightening. I have to struggle with it, I confess. When I look at that proof, I don't come away like I did with simple Vitali. Simple Vitali, you look at the proof, you say, oh, wow. In full Vitali, you look at the proof and you say, okay, yeah, okay, it's true. Right, but I don't feel inspired by it. And I was hoping to somehow get away with, maybe not needing for this first introduction to use the Vitali covering lemma too much. And if you're in love with Vitali covering, I understand, but I kind of felt for a first course that it wasn't the greatest theorem. All right, now where am I going to use it though? And that comes into these issues of differentiation. So let's go back to just definition of bounded variation. What's the bounded variation of function? Right? We learned this in our first course on real analysis. You take your function, choose a finite partition, finitely many point, and count and just add up how much the height changes, taking everything positive at those points. Take the soup, that's the total variation. If that's finite, then you have bounded variation. So it's like, climbing up a mountain. And you go up and then you have to go down into the valley, and you go up again, you go down, up, down, up, down, up, down, and you count all the ups and downs positively. And you only worry about height. So how much height did you actually traverse to get up the mountain? And the neat thing is that if you have such a function of bounded variation, you can write it as the difference of two monotone increasing functions. And the proof of this is really neat. I'm not going to write it out, but basically you kind of in a really neat way just take out the positive parts, right, of the variation and just put them in one place. And the negative parts, you separate them over to the other function. And then the two parts together make the original function. So in the end, monotone functions are just, there's nothing to them. They're just, right? They're just different, bounded variation functions. There's nothing to them, right? They're just the difference of two monotone increasing functions. And how hard can it be to analyze a monotone increasing function? It just can't be that hard, right? How bad can it be? Right? Okay. So this is what I failed at. The theorem is monotone increasing functions are differentiable almost everywhere. and you look at it and you say, oh, of course, right? How hard can they be? But as you know, you can create all kinds of really strange examples of monotone increasing functions. And it's a lot harder than it looks. And this is the proof of this fact right here. This is the one that I feel is the most difficult proof in the entire first course on real analysis. And I worked really hard to try to find a simple proof or an enlightening proof, even a long but enlightening proof I would be satisfied with. Now, there are a number of different techniques that you can use to get at this. And I looked at the different techniques, and I eventually gave up and went with essentially the standard technique that uses the full Vitali covering lemma. So already, Vitali covering lemma, I'm not feeling real great about its proof, although it's in essence a greedy algorithm. Okay, I can live with that. You get into the details of this proof, and it's just long, and you get a Vitali cover by looking at these Dini numbers, and I come away from that proof saying, what did I do? I don't really get the insight. Why did it work? You can go through and understand it, but this is the one that I felt I'm most disappointed with. This is the one that directly used Vitali covering. On the other hand, it ended up being the only proof that I had to use Vitali covering for. And although there are other results that typically are proved using Vitali covering, and one of them is at the bottom, I'll talk about this one later on. Standard result that if you are both singular and absolutely continuous, then you have to be constant. Standard proof is a Vitali covering lemma proof. I was able to do it without that. And everything else, I felt that there was an enlightening proof to it. Now, Vitali covering and this, right, they're there. It's just, I'm going to use this theorem, and so I am using Vitali covering in the development of the text, but it's going to be buried a little bit because we're not going to use it again. So now we get to absolute continuity. And to remember what the definition of that is, a function on an interval a to b is absolutely continuous if for every epsilon there's a delta, so that when you take non-overlapping subintervals, aj, bj, and they're very small, right? The total sum of their length is small. Then the sum of the absolute value of f of bj minus f of aj has to be less than epsilon. So this is a generalization of the idea of continuity. Continuity is just this with one interval. And now, if you've got a small interval, 2 points close together, then f of the points has to be close together. And now you're just refining that and allowing yourself to split up one interval into lots of little pieces that can be anywhere. They don't have to be close to each other. Like one interval, right? Now you can split it in half and put take two little intervals that are far apart, and you still have to have this property. So it's stronger than continuity. And of course, now we've all been through the first course. We know that these are the functions for which the fundamental theorem of calculus holds. Now, straight off, the easy parts, well, easy, I am using that terrible theorem that relied on Vitali covering to prove that monotone functions are almost everywhere differentiable, because absolutely continuous functions have bounded variation. That's easy. And then by the Jordan theorem, nice, beautiful proof. Bounded variation functions are the difference of two monotone increasing functions. So I am using that. But that, plus a few other basic properties of the Lebesgue interval, tell us that if we take an integrable function g on L1, in L1 of the interval, and just form its antiderivative. So capital G of x is the integral from a to x of little g. Then this function is absolutely continuous. And just direct computation, we know that if you have an integrable function, then its values, the integral on a small set is going to be small. And so you just use that and you see that capital G is absolutely continuous. Then by the almost everywhere differentiability theorem, we apply that and get that this antiderivative is differentiable. And its derivative belongs to L1. That still leaves open the question, does the fundamental theorem of calculus hold? Is the derivative of capital G this function little g? And that takes work. But what I hope to show you in the rest of the talk is it's fun work. And I want to show you some things called growth lemmas that I think are really neat. I call them growth lemmas. And to motivate this, let's just go back again to a really standard blow-up exercise. If you have a function that's Lipschitz on AB, Lipschitz constant K, then how much does F blow things up by, right? You take a subset of AB as some measure. How much does that measure get blown up when you run it through F and get the image, F of E? And the answer is no more than a factor of K, the Lipschitz constant. And the reason is nice. You just cover your set by intervals, right? Approximated by intervals, the union of intervals. And then the Lipschitz just tells you how much the interval gets blown up by, no more than a factor of K. So each interval just gets blown up by that much. Okay. And therefore it carries over to the measure of arbitrary sets. Okay, but we're going to come to an issue where later on, where I don't have Lipschitzness. All I know is something like F is Lipschitz on a set E, not everywhere on the interval, just one particular set E, it's Lipschitz on. What happens to that, to the measure of that set? And so if you try to do this approximation argument, right? So, well, you approximate by intervals, the points don't have to be in the set anymore. You don't know that what happens to the endpoints, what happens to your intervals? You just don't know anymore. So what can you say? And there's a beautiful theorem. This is the first of two growth lemmas, as I like to call them. And it's kind of the expected result. I mean, suppose that you were Lipschitz on this set, or more precisely, let's suppose that you're differentiable on this set and the derivative is bounded on the set, right? Let capital M be the soup of the absolute value of F prime on this set. Then how much do you get blown away? Well, no more than M. I look in lots of texts. Almost nobody has this result. It's a beautiful result, though. I mean, it's just, it's expected. It's neat. I'm going to discuss the proof a little bit. What I've looked too many places. I forget where I found things out nowadays. As when I wrote my book, I credited it to a paper of Warburg that came out in 1965. And that was the first published proof that I could find. And I was joked with my students, it's really kind of amazing that, we think of most of these theorems as being proved way back when. And 1965 is not that long ago, at least not to me. It's a long time ago for my students, but not so much for me. And Warburg, he says he found it as an innocent problem in Nathanson's book, which came out in 1955. And so in my text, that's what I credit it to. But then I went back and I looked at John's book, which has so many neat things in it. And of course, John does have this in there. And I knew it was in John's book. But I hadn't paid enough attention to what he said about it. Because John points out that this can be found way back in a 1937 text by Sachs. So it's older than I gave it credit for. But still, nobody knows it. And hardly anybody refers to it. And I just think it's a really neat result. The proof, I just said you can't use that covering by intervals argument. But the proof, one way to do it is you very cleverly adapt that. In a certain way, you choose each point in E and you find an integer that goes with that. And then you take all the points whose associated integer n sub x is less than or equal to n. Now this set, right, you're doing this point by point. So this set is not necessarily going to be measurable, right? And I'm not going to try to prove that it's measurable. But every point in E f is differentiable at that point. And because of that, these sets En increase to all of E. I'll show you what n sub x is in a second. But these sets are nested in increasing. And you approximate them by intervals. And you also use the really neat fact that continuity from below holds for exterior Lebesgue measure, not just for measurable sets. And I always assign that as a homework exercise. I think it's a really neat application of the basic facts about Lebesgue measure, that continuity from below holds for exterior measure and not just for measurable sets. This is an actual real life application of that, which I think is nice. What are these sets, these numbers n sub x? You fix a point x, fix an epsilon. You know you're differentiable at that point. And so if you get close enough to that point, then you'll have a Lipschitz condition. So if you're closer than 1 over n sub x, then f of x minus f of y will be no more than that sup plus epsilon times the distance between x and y. Okay, and the proof is a little longer than I want to put on here, but it's just kind of neat. And I like it. And from that, let's go on and do the second growth lemma. And this also, I thought was first done in a paper by Warburg, but John correctly points out that it at least goes back to this text of Sachs in 1937. And again, it's a blow-up. So you take a set E in your interval, and you want to know how much is it blown up by? Well, the derivative is, telling you something about how much things are increasing. It's natural that the derivative should come into play. And what this theorem tells you is, if you take a measurable subset of an interval, and if all you know is that f is differentiable at points in that set, then the measure of the image is no more than the integral of f prime, absolute value, on that set E. And I want to take you through this proof. Right? So you've got control on the blow-up. And how does it work? Well, it just applies the growth lemma 1. Growth lemma 1 told you, let me just go back to it. Growth lemma 1 tells you that if you're differentiable on a set, and you know that the f prime is bounded by m on that set, then you have control on the size of the blowup. So what we do is we just take E and we divide into the regions where f prime is between k minus 1 epsilon and k epsilon. Every point in E is different. F is differentiable, so f prime has to be something. So every point in E is in one of these sets EK, and we just quantify which region it's in. These sets they're measurable, they're disjoint, their union is E. So the sum of their measures is all of E, and we just work piece by piece. Growth lemma 1. Since f prime is less than k epsilon, we know that the image of EK is blown up by no more than a factor of k epsilon. And now just do the calculation. How much does the whole thing get blown up? Split into the pieces. Right? Split into the pieces right here. And on each piece, apply the growth lemma. You know that f prime is no more than k epsilon. So the measure of the image of EK is no more than k epsilon times the measure of EK. Growth lemma 1. And then, I love this proof for the next trick. Every once in a while, you do something that's, just so stupidly simple that it's profound. And on the next line, you write k is equal to k minus 1 plus 1. And you split the k epsilon into k minus 1 epsilon plus epsilon. And then apply the definition of EK again. F prime is greater than or equal to k minus 1 epsilon on EK. So k minus 1 epsilon times the measure of EK is less than or equal to the integral on EK of f prime. And then you've done that on each set EK. So the sum of all those pieces is just the integral of f prime. And there was an epsilon left over, right? But that's okay, because this holds for every epsilon, and we get that the measure of f of E is less than or equal to the integral of f prime, right? Just two fun proofs. And that leads us to another theorem that nobody puts in their text, and I don't know why. It's a beautiful theorem. It's called the Banach-Zaretsky Theorem. Sometimes people have pieces of it, but very few texts actually quote this outright. And what it does is it gives us an equivalent conditions to being absolutely continuous. What is the same as being absolutely continuous? Okay, Banach-Zaretsky says that's the same as being continuous, having bounded variation, and mapping sets of measure 0 to sets of measure 0. And it's also the same as being continuous, differentiable almost everywhere with an integrable derivative, and mapping sets of measure 0 to map sets of measure 0. That's what continuity is all about, absolute continuity. From this point of view, it's continuity plus a little something extra, either bounded variation or being differentiable almost everywhere. And then a third piece, mapping sets of measure 0 to sets of measure 0. That condition, sets of measure 0 goes to sets of measure 0. That's sometimes called Lusin's condition. And it's important because if you're continuous and you map sets of measure 0 to sets of measure 0, then you map measurable sets to measurable sets. So all these absolute continuous functions are mapping measurable sets to measurable sets. And if you look back Cantor-Lebesgue, you know, right, you can take a set of measure 0 and map it to a set that has positive measure. And you can map a measurable set to a non-measurable set by the Cantor-Lebesgue function. So this is telling you something really important about these absolutely continuous functions. And from the growth lemmas, here's the proof of one of the implications. Just assume that you're continuous, differentiable almost everywhere. You have an integrable derivative, and you map sets of measure zero to sets of measure zero. Okay. Take a set where f is differentiable, call that D. And then absolute continuity was something about non-overlapping intervals. Well, we'll do a calculation for one subinterval, and then all you have to do is just paste these together for the general case. So choose one subinterval, CD, and divide the interval C to D up into two parts. The part where f is differentiable, call that B, and the part where f is not differentiable, call that A. We've assumed almost everywhere differentiability, so A has measure zero. You're differentiable on B, so you can apply the growth lemma. How much then, okay, to prove you're absolutely continuous, you have to show that something about f of D minus f of C, okay? So how big is that? Well, f of D minus f of C absolute value. By the intermediate value theorem, the interval from C to D, when you look at its image, it contains those 2 points. And so by the intermediate value theorem, it contains everything in between. So that the length of that interval from f of C to f of D is less than or equal to the length of the image of CD under F. So just look at the image of the whole interval. And the interval is made out of A and B. So you split into those two pieces. And on B, you're differentiable everywhere. So you use that growth lemma. And you get that it's bounded by the integral on B of F prime. And A has measure zero, so F maps it to a set of measure zero. So that part goes away. And so you get an estimate here that f of D minus f of C is less than the integral of F prime on that small interval CD, and that's going to be tiny. And then you just put, okay, you've got finitely many of those, or countably many of those, right, the subintervals, and you just add them all together. And you get absolute continuity from it. So it's a very short, beautiful application of the growth lemma. And I have it written out here to get to the final parts, but let's look at the corollaries we get out of this. First corollary, if you have a function that's differentiable everywhere on the interval and f prime is integrable, then you are absolutely continuous. And this comes straight from Banach-Zaretsky, because all you have to do is show that sets of measure zero map to sets of measure zero. That's the only thing missing to apply Banach-Zaretsky. And the growth lemma tells you that if you, okay, how big is the image of f of A? It's bounded by the integral of f prime on A. Well, if A has measure zero, then that integral has measure zero. So Banach-Zaretsky immediately pops out this corollary. Now that corollary requires differentiability everywhere. What if you were only differentiable almost everywhere? Well, there could be a problem trying to apply Banach-Zaretsky, because it might no longer be true if you don't, right? You don't already know that you're absolutely continuous. You're trying to prove that. You might have a situation where sets of measure zero get blown up to sets of positive measure. On the other hand, there's one situation where I'm sure that the image will have measure zero, and that's if you use countable sets. The image of a countable set is still going to be countable no matter what f is. So that's going to be measure zero. And so you can get a corollary where you say, okay, suppose that you're differentiable at all but countably many points with integrable derivative. Then pop straight out of Banach-Zaretsky that you are absolutely continuous. This is a really nice result. And if you look at Fallon, he has a whole paragraph about this. And he says this is a corollary 2 here that just popped out from Banach-Zaretsky. Tholen calls this a highly non-trivial theorem. And, okay, people are missing these beautiful theorems here with just fantastic applications. Next corollary that just kind of pops out is this result about if you're absolutely continuous and singular, then you must be constant. Why? Okay, let E be the place where f prime is 0. That's a set of full measure, right? Let Z be the leftover. Okay. Z has measure 0. So if you're absolutely continuous, Z gets mapped to a set of measure 0. And where does E get mapped to? The growth lemma tells you that the image, measure of the image, is controlled by the integral of f prime on that set, but f prime is 0. So the image of that set, the image of the set where f prime is 0, has measure 0. Together, E and Z are the full interval. So the full interval gets mapped to a set of measure 0. Well, the image of the full interval, that's another name for the range. This function has, its range has measure 0. But it's a continuous function, right? So its range is either an interval or just a single point. And it, therefore, since it has measure 0, it has to be a single point, and therefore f is constant. So we don't need the Tholen covering lemma to prove this corollary. And what else pops out? The fundamental theorem of calculus, which says that 3 things are equivalent, right? F is absolutely continuous if and only if f of x minus f of a is the antiderivative of some L1 function g. And that's equivalent to being differentiable almost everywhere with integrable derivative, and f of x minus f of a is the integral from a to x of f prime. And I'll take you through one implication here. Assume that you are absolutely continuous, and let's go for that third one. So if you are absolutely continuous, we know that the derivative exists, and we know that it's integrable. And we know that the antiderivative, call that capital F. Capital F of x is the integral from a to x of f prime. Okay, that's an absolutely continuous function. And Lebesgue differentiation, which, by the way, used simple Vitali, Lebesgue differentiation tells us that capital F prime is little f prime. So capital F prime, the antiderivative, capital F, the antiderivative of f prime, its derivative is the same as the derivative of f, right? Capital F prime is little f prime almost everywhere. And therefore, capital F minus f derivative is 0 almost everywhere. But capital F minus f is an absolutely continuous function. So I proved that it's absolutely continuous and singular, and therefore it's constant. And so the whole beautiful fundamental theorem of calculus just flows from these growth lemmas and the Banach-Zaretsky theorem. And that is something that just people don't seem to be aware of. It's just not in very many texts. And that is the part that I feel I really succeeded at. Is I don't take credit for this. I didn't do any of this, but just putting it in the down on paper as a really nice, beautiful way to get to the fundamental theorem of calculus. Okay, so I failed back at differentiability of monotone functions. I had to give up on that, but some of these other things came through very nicely. So with that, I want to thank John for introducing me to absolute continuity and for his wonderful text that Wojtek also helped bring back with a new edition, and just say thanks and thank you, everybody.
Thank you, Chris. Thank you very much for a great enlightening talk. Ladies and gentlemen, please feel free to unmute yourself and ask questions.
I'd like to make a comment. First of all, Chris, that was a brilliant talk. Thank you very, very much. I know I suffered in my proof of Banach-Zaretsky back in the 70s, so what you wrote is also brilliant in my opinion. And the idea of the growth lemmas, I think we should now call them the Heil lemmas or the Heil growth lemmas. That's a fantastic idea. Thank you very much.
So I have to confess, the growth lemmas, the papers by Warburg are very nice, and part of the proof that I gave is coming straight from Warburg's paper. I didn't know about Sachs until much later, so I haven't gone back to try to see how those proofs back then go. But there is one book that I should give credit to, and that's a book by Bruckner, and Thompson, where they do their real analysis. And it's a rather dense and encyclopedic book, but they do Banach-Zaretsky, and they do it at they do various more general terms than what I did here. It's a difficult read, but that's where I got part of the proofs from, is that text.
I don't know that book. When was it published?
See if I've got it. I'll have to dig it out.
Okay, I'm interested to know.
Oh, here it is. Here's the